Products such as large cranes, ship hulls, or shipyard ramps all have something in common. They are all massive assemblies of metal parts all welded together. And because of this, they share some of the same design and engineering characteristics. Engineers typically will try to predict stress distribution throughout the structure and the final assembly capacity to carry loads. The structure's performance is then typically optimized through design iterations. Engineers will either affect the shape or position of load-bearing members to change the overall load path through the structures. Until today, finite element analysis has been out of reach for most engineers. It requires expert skills and multiple tools. And so, for much of their superstructure design studies, engineers still often rely on more approximate methods. And this leads to oversized parts, increased weight, and higher raw material cost. MSC Apex does not require any specialized training, and it integrates all the design and analysis tools you need in a single user interface. Direct modeling, for example, makes it very intuitive to change parts shapes and move components around. And with the Apex solver, users can perform model, buckling, and linear static stress analysis all in one integrated tool. With finite element simulation, one can fully capture the 3D response, make accurate stress and limit load predictions, and build a more optimal, cost-effective structure. Typical CAD geometry is not suitable for simulation and requires many tweaks, simplifications, and repairs. Superstructures tend to have hundreds, sometimes thousands of parts and connections, and modeling tasks can take up to weeks or even months to complete. MSC Apex automates many of these time-consuming tasks, such as creating mid-surfaces, applying appropriate thicknesses properties to mid-surface geometry, or connecting parts together, whether with mesh-dependent or mesh-independent connections. MSC Apex also automates defeaturing operations for any standard or user-defined features. One key innovation is the integration of geometry tools with meshing algorithms that completely eliminates the need to hand off data between CAD and CAE systems, and it streamlines the geometry cleanup process. Traditionally, CAE systems are parts and assembly agnostic for a good reason. The FE solvers that they rely on flatten the assembly structures into one monolithic model before processing the data. Unfortunately, superstructures typically have deep product structures and are much better suited for incremental validation of parts and subassemblies before simulating the entire assembly. MSC Apex is a parts-based solution. Both the user interface and the solver methods are parts and assemblies aware. Engineers can then adopt a divide and conquer approach and incrementally build and validate their models, starting with parts, then subassemblies, before building the complete assembly. Also, the parts-based solver generates parts individually and reuses unchanged parts during incremental runs, which speeds up execution. Changes to the design typically requires additional time spent for modeling and model validation tasks. The repeated work of remeshing, reconnecting parts, reapplying loads, etc. is much error-prone and quite time-consuming. As a result, engineers only manage to cover analysis for a few design iterations. Now, Apex allows for ultra-rapid results updates. All the objects in MSC Apex, from the geometry, the mesh, the loads and the scenarios, are all coded into a single dependency chain that the software silently continuously updates for the user. This way, any changes to the design, whether a change on the shape or size of a part or a change in the assembly layout, all can be managed autonomously by the application. The model will automatically regenerate, and the user is at every moment only one click away from regenerating simulation results.